Hello friends, you are watching ISC Mathematics and we are solving exercise 1.1 of NCERT Mathematics textbook. Okay, the chapter title is Relation and Functions. In the last video we have solved up to question number 3. Now today we will begin from question number 4. So that the relation R, relation R is defined as an ordered pair A comma B such that A is less than or equal to B. We have to show that this relation is reflexive and transitive but not symmetric. Okay, we have to show that that the relation R is reflexive and transitive but not symmetric. Okay, let us check the reflexivity. Okay, for all A belongs to R. Okay, here R is a set of real numbers. Relation R is defined on R, that is set of real numbers. So for A belongs to R, A is less than or equal to A is true, yes or no? Because obviously A is at least equal to A. We know that every number is equal to itself, and therefore we have ordered pair AA, BB, CC or 1 1 2 2 3 3. Such all these types of ordered pairs will be present in R, and therefore we will write that R. Okay, therefore we will write for that A comma A belongs to R, and therefore R is reflexive. Clear? Now let us discuss symmetricity. Okay, in symmetricity we will take two elements for all A and B belongs to R, set of real numbers. Here one ordered pair is there. A comma B belongs to R implies A is less than or equal to B. Okay, but B less than or equal to A is not always true. Yes or no? For example, here we can give one example. 1 comma 2 belongs to R because once 1 is less than or equal to 2. Okay, this inequality is satisfied by this ordered pair. Okay, but 2 is not less than or equal to 1, and therefore 2 comma 1 does not belong to R. Clear? Yes or no? It implies what? B comma A does not belong to R. A comma B belongs to R, but B comma A does not belong to R, and therefore we will write that R is not symmetric. Clear? So far we have discussed the reflexivity and symmetricity. Now we will discuss transitivity. Transitivity. Okay, for transitivity we will take three elements in R, set of real numbers for A, B and C belongs to R. R is a set of real numbers. Clear? Two ordered pairs are present in R. We will consider two ordered pairs A, B and BC in R. So A comma B belongs to R implies A is less than or equal to B, and B comma C also belongs to R, it implies B is less than or equal to C. So from 1 and 2 we can say that A is less than or equal to B and B is less than or equal to C. It implies A is less than or equal to C, which implies A comma C belongs to R. So if A comma B and B comma C belongs to R, then by definition A comma C must also belong to R. So we have proved, and therefore we can say that this relation is transitive. Clear? So let us write down over here. Therefore R is a transitive relation. Clear? Okay, so question number 4 is completed. Now we will solve question number 5. Okay, now question number 5. We have to check whether the relation R is defined by A comma B such that A is less than or equal to BQ, and relation R is defined on R. What is R over here? This is set of real numbers. Clear? We have to check whether it is reflexive, symmetric or transitive. So we will check all the three one by one. Okay, first we will check reflexivity. Okay, now we know the method. We will consider one element from R. For all A belongs to R, R is real number, set of real numbers. Okay. A is less than or equal to A cube is not always true. Yes or no? For example, 1 by 2 is less than or is not less than or equal to 1 by 2 the whole cube. Yes or no? Clear? Because 1 by 2 the whole cube will be 1 by 8, and actually 1 by 8 is less than 1 by 2. Clear? So this inequality does not hold true for 1 by 2 belongs to R. Okay, and therefore we can write down that 1 by 2 comma 1 by 2 does not belong to R. Okay, this is only one example, and therefore we can write A comma A does not belong to R for all A belongs to R. Here this second R, when we write A belongs to R, here R means set of real numbers. Clear? So A does not belong to A comma A does not belong to R. It means R is not reflexive, and therefore relation R is not reflexive. Now let us check symmetricity. real numbers, suppose if ordered pair A comma B belongs to R, okay, it implies the condition is satisfied, that is A is less than or equal to B cube. Yes or no? For example, for 1 comma 2, 1 is less than or equal to 2 raised to 3 is right, but 2 is not less than or equal to 1. Yes or no? But 1 is less than or equal to B cube is not always true. Yes or no? Let us give example. For example, for 1 comma 2 belongs to R, 1 is less than or equal to 2 cube, but 2 is not less than or equal to 1 cube, and therefore 1 comma 2 belongs to R, but 2 comma 1 does not belong to R. Yes or no? And therefore A comma belongs to R, but B comma A does not belong to R. Okay, and therefore the relation R is not symmetric. Clear? Understood? So we will write down over here that the relation R is not symmetric. Okay, and therefore R is not symmetric. Clear? Now let us check transitivity. Okay, here 3 elements A, B and C belongs to R, set of real numbers. 2 ordered pairs are present. We will consider that A and B belongs to R, implies A is less than or equal to B cube. Okay, and B comma C belongs to R, implies B is less than or equal to C cube. But A is less than or equal to C cube is not always true. Okay, let us take one example. In such cases, okay, where this theoretical explanation is not sufficient, you should give one example. Okay, so let us give here one example to explain transitivity. Okay, for example, for 9, 3 and 2 belongs to R, 9 comma 3 belongs to R, it implies 9 is less than or equal to 3 cube. Yes or no? Yes or no? This is right. Okay, and similarly 3 comma 2 belongs to R, it implies 3 is less than or equal to 2 cube, because 2 cube will be 8. But 9 is not less than or equal to 2 cube. Okay, because 2 raised to 3 will be 8, and 8 is not less than or equal to 9. Clear? 8 is yes or no? 9 is not less than or equal to 8, and therefore we can say that 9 comma 2 does not belong to R. A comma B belongs to R, B comma C belongs to R, but A comma C does not belong to R. Yes or no? Implies A comma C does not belong to R, and therefore we will say that R is not transitive. Okay, so this relation is neither reflexive nor symmetric nor transitive. Clear? Okay, now let us solve the next question, that is question number 5. Question number 5 we have completed. Now we will solve question number 6. Okay, let us solve question number 6 now. In question number 6, we are given a set. Name is not given. Let us name this set to be set A containing 3 elements 1, 2, and 3. The relation R is defined on A, and R is given by the in terms of ordered pairs 1, 2, 2, 1 is symmetric but neither reflexive nor transitive. Okay, so it is very evident because here 1 comma 2 belongs to R. Okay, that is A comma belongs to R, and its reverse pair 2 comma 1 also belongs to R, and therefore this is symmetric. Yes or no? R is symmetric. Okay, but here 1 comma 1, 2 comma 2, and 3 comma 3 does not belong to R, and therefore R is not reflexive. Clear? For symmetricity, what is the condition? If you have a reverse pair, if you have an ordered pair AB, then we have to check its reverse pair. So 1 comma 2 is there, so 2 comma 1 is also there. So condition of symmetricity is satisfied, but recall the definition of reflexivity. For ABC belongs to given set, if AA, BB and CC are present in a relation R, then only it is reflexive. So if we have 3 elements, then each element there must be an ordered pair of each element with itself. For example, 1 with 1, 2 with 2, and 3 with 3. So these 3 ordered pairs at least are required to be present in R, then only it will be reflexive, otherwise not. Clear? Okay, similarly you can check the transitivity. Okay, so for transitivity we will check like this: AB and BC. Yes or no? Here we have also 1 comma 2 belongs to R, and 2 comma 1 belongs to R, but if AB and BC are there, then the third pair AC must be there. That is, what is the third pair? 1 comma 1. Okay, but that is not present in R. 1 comma 1 does not belong to R, and therefore R is not transitive. Clear? Okay, so here we have 2 pairs of the form A comma B and B comma C. So we must have A comma C. 1 comma 2 and 2 comma 3 are there, so we will check for 1 comma 1 in R, but you will notice that 1 comma 1 is not present in R, and therefore it is not transitive. Clear? So this relation is only symmetric, but it is neither reflexive nor transitive. Let us solve the question number 7. Okay, what is there in question number 7? A relation on set A is defined. Okay, set, what is set A? It is the set of all the books in a library. Okay, let us write down that set A is a set of all the books in a library, okay, of a college, and relation R is defined on A. Definition is given. R is defined such that x comma y, R is a relation containing all the ordered pairs x comma y such that x and y have the same number of pages. X and y have the same number of pages. Clear? This is the relation. Set is what? Set is a set of all the books in a library in a college. Okay, so okay, we have to show that it is an equivalence relation. It means it is reflexive as well as symmetric as well as transitive. So we will discuss the three properties one by one. First we will discuss reflexivity. So here we will take a book for X belongs to given set A, where X is a particular book. Yes or no? Okay, we can write this statement that X and X have the same number of pages. X and X have the same number of pages, because we are discussing about a single book. Suppose you have taken any book of mathematics, then that book, okay, suppose that contains 100 pages. So book X and X, so we are referring to the same book, yes or no? So 100 pages will only be there, clear? So X and X have the same number of pages. That is always true for all the books present in a library, clear? So, and therefore we will write that X comma X belongs to R, and therefore R is reflexive. Then number 2 we will discuss now symmetricity. Okay, now symmetricity, we are taking two books X and Y from the library for all X and Y belongs to set A, yes or no? Such that X comma Y belongs to R. It implies what? We have selected two such books that they have the same number of pages. So here X and Y have the same number of pages. X and Y have the same number of pages. So we can write the reverse of that. If X and Y have the same number of pages, it implies Y and X have the same number of pages. Yes or no? It implies Y and X have the same number of pages, and which implies Y comma X belongs to R. So X comma Y belongs to R implies Y comma X belongs to R, and therefore R is a symmetric relation. Clear? So R is reflexive, R is symmetric. Now we will prove that R is transitive, and hence from the three results we can say that R is equivalence relation. Now let us prove the transitivity. Okay, what is transitivity? So for transitivity we will take three books X, Y, Z in A. For X, Y and Z belongs to A. Okay, two pairs X and Y, two books we have taken in R such that X and Y have the same number pages. Okay, this is result 1. Another pair we will take Y comma Z, two books Y and Z such that Y and Z have the same number of pages. Okay, here I will write down Y comma Z belongs to R. It implies Y and Z have the same number of pages. Clear? So from 1 and 2, if x and y have the same number of pages and y and z also have the same number of pages, it implies that x and z will have the same number of pages, yes or no? So it will imply that x and z have the same number of pages, and it will imply x comma z also belongs to R, and therefore x is transitive. Clear? Therefore we will say that R is transitive. Okay, now since R is reflexive, symmetric and transitive, it is equivalence. Finally another statement we will write down. Since R is reflexive, symmetric and transitive, and therefore it is equivalence relation. Clear? I hope you have understood this question. Now let us solve question number 8. Okay, so we will solve now question number 8. Here set A is given containing elements 1, 2, 3, 4 and 5. Okay, relation R is defined as a relation containing ordered pair A comma B such that A minus modulus of A minus B is even. Okay, now this is an equivalence relation. Another parts are there in the question, but the first part is we have to prove that this is an equivalence relation. Yes or no? So let us prove the equivalence. Now we know that in order to prove the equivalence, we need to prove reflexivity, symmetricity and transitivity. So we will begin with reflexivity. Okay. Reflexivity. Okay, now the ordered pairs will be from A by A. That is, you will have 5 by 25 ordered pairs starting from 1, 1, 1, 2, 1, 3, 1, 4, 1, 5. Then 2, 1, 2, 2, 2, 3, 2, 4, 2, 5. Yes or no? 3, 1, 3, 2, 3, 3, 3, 4, 3, 5. 4, 1, 4, 2, 4, 4, 4, 3, 4, 4, 4, 5. And similarly 5, 1, 5, 2, 5, 3, 5, 4, 5, 5. So this 25 ordered pairs we will have. Clear? In A by A. Now we will check each ordered pair. This is the formula given. For example, you are taking 1 comma 1. So 1 minus 1 is 0. Now 0 is obviously an even number. Clear? Similarly, if you take 1 comma 2, so 1 minus 2, but modulus of 1 minus 2 is equal to 1. Yes or no? Reflexivity we are taking. So in reflexivity, we will consider only the pairs which are 1, 1, 2, 2, 3, 3, 4, 4 and 5, 5. These 5 pairs we have to check, and for each pair we know that 1 minus 1, 2 minus 2, 3 minus 3, 4 minus 4 or 5 minus 5. Each answer is 0 and 0 is an even number. Therefore we will say that R is reflexive. So we will write down over here, okay, for each of the ordered pairs 1 comma 1, 2 comma 2, 5 comma 5, okay, modulus of a minus b will be equal to 0. Yes or no? Which is an even number. Yes or no? Is equal to even. We can write. You can give an example. For example, you take 1 minus 1 is equal to 0 is equal to 2 minus 2 is equal to so on is equal to 5 minus 5. Okay, so all these differences are 0 and 0 is an even number, and therefore we can say a comma a belongs to R for all a belongs to set A, and therefore R is reflexive. Number 2, we will explain now symmetricity. Okay, now in symmetricity, remember that the ordered pairs which are to be taken are such that they satisfy this condition. Means we will not take all the 25 ordered pairs, only those ordered pairs which satisfy the given condition, that is the modulus of the difference must be even. So obviously odd pairs will come and even pairs will come. Odd, even, even. Odd, even will not come. For example, 1 comma 2 will not come because 1 minus 2 or 2 minus 1 is not even. Yes or no? So only odd pairs. For example, 1 3, 1 5. Yes or no? And even pairs. Even pairs will come like 2 4. Clear? Yes or no? 2 2 2 4 we will not take because 2 2 4 4 we have already taken. Similarly 1 1 3 3 5 5 also we have taken. Oh, and those also come in symmetricity. Yes or no? So odd pairs, which are the odd pairs? 1 1 1 3, 1 1 3 3 5 5, and 1 3 3 1 3 5 5 3, like this. Clear? So these all the ordered pairs will satisfy this condition because the difference of two odd numbers is even. Yes or no? Clear? So here you will write down that for all a comma b belongs to R. Okay, a comma b for all a comma belongs to set a comma b belongs to R. It implies a minus b is even. It will implies modulus of b minus a will also be even. Yes or no? It is very clear because the modulus will remain same only answer in the modulus whether you take a minus b or b minus a. So if 1 minus 3 modulus is 2, then 3 minus 1 is again 2 only. Clear? So you can give one example, one or two example. For example, 1 comma 3 belongs to R. 1 minus 3 is equal to 3 minus 1 is equal to 2 is equal to an even number. Similarly, one even pair you can take for 2 comma 4 belongs to R. Modulus of 2 minus 4 is equal to 4 minus 2 is equal to 2 is equal to again an even number. Clear? Yes or no? So if 1 comma 3 belongs to R, then its reverse pair also 3 comma 1 will belong to R. Similarly, if 2 comma 4 belongs to R, then its reverse pair 4 comma 2 also belongs to R. Clear? Yes or no? So we can say that this relation is symmetric. Clear? Yes or no? Here let me write down 1 comma 3 belongs to 3 comma 1, and here we will write 4 comma 2 belongs to Clear? And therefore finally if we write down, therefore, okay, if A minus B belongs to R, it implies B comma A. If A comma B belongs to R, it implies B comma A belongs to R, and therefore R is symmetric. Okay. Clear? Another way is you find out all the ordered pairs satisfying the condition, and then each ordered pair you can explain. Clear? Or we can explain in this manner also using the definition and giving one or two examples. Now reflexivity and symmetricity is done. Now we will explain the transitivity. Now let us explain what is transitivity. Whether transitivity is satisfied or not. Okay, number 3, transitivity. Yes or no? So obviously for all A, B, C belongs to set A comma B belongs to A. Relation R, it implies magnitude or modulus of A minus B is even, and another order pair B comma C belongs to R, it implies B minus C is even. Okay, so from 1 and 2, we can write that A minus C will also be even. It will imply A comma C belongs to R. Now let us give one example. So for this, let us take the 3 odd numbers. For 1, 3 and 5 belongs to set A, 1 comma 3 belongs to R, implies modulus of 1 minus 3 is equals to 2 is even. Yes or no? Again 3 comma 5 belongs to R, it implies modulus of 3 minus 5 is equals to 2 is also even, and then okay, it implies now 1 minus 5. We will take the order pair 1 comma 5. So modulus of 1 minus 5 is equal to 4 is also even. Yes or no? Which implies 1 comma 5 belongs to R. Okay, so with the help of example we have explained. So and therefore we will write down R is transitive. Okay, and hence since R is reflexive, symmetric and transitive, therefore R is reflexive. Okay, so we have proved the reflexivity. Now let us check the other questions given in the same question number 8. Okay, we have to show that all the elements 1, 3, 5 are related to each other, and all the elements 2, 4 are related to each other. Yes or no? So we can show. Okay, let us show that if equivalence you understood how to prove. Now another question in the same question number 8. Okay, it would be better now to find out the R. Okay, we can find out R. Okay, using this, it will not take time. 1, 1, 2, 2, 3, 3, 4, 4, and 5, 5. Okay, these 5 ordered pairs will come. Then odd 1, 3, 3, 1, 1, 5, 5, 1. Okay, then 3, come in R. I don't think that any other ordered pair is left. Okay, 1 3 and 1 5, then 3 5 we got and 2 4 we got. Okay, done. Clear? So now the question is that you are given a set 1 3 and 5, and we have to show that all the elements of the given set are related to each other. Okay, if all the elements of given set are related to each other, it means all the ordered pairs. Suppose if we name this set as set B, let us name this set as set B. Okay. So what is the meaning of this statement? All the elements of the given set are related to each other. It means B by B. Okay, that is the cross product of B with itself. Okay, that will be, it means 9 elements. Which are the 9 elements? 1 1 3 3 5 5. Okay, 1 1 1 3 1 5, 3 1 3 3 3 5, and 5 1 5 3 5 5. These all the 9 ordered pairs must be there in R. So see, 1 1 1 3 1 5, then we have 3 1 3 3, there is 3 3, okay, here, and 3 5, okay, similarly 5 1 is here, 5 1 5 3 and 5 5. Okay, so these all the 9 ordered pairs are present in R. Clear? So we will write down here, since all the ordered pairs of B by B are present in R, and therefore all the elements of set B are related to each other. Yes or no? So in this way simply you can explain. Find out all the ordered pairs of R, then show that if you need to show that all the elements of B are related to each other, it means you have to show that B by B is present in R. So that we have shown by writing that all the elements of set all the ordered pairs of B by B are present in R, and therefore all the elements of set B are related to each other. Similarly, another set C is given set of even numbers. Okay, here you have to show that all the this is a question. Okay, and similarly here this is another question, that all the elements of C are related to each other. Okay, now how to show? Obviously, if you want to show that all the elements of C are related to each other, it means you need to show that C by C, that is 4 ordered pairs, 2 2 2 4, 4 2 4 4. These 4 ordered pairs must be present in R. So see, 2 2, then we have 2 4 and 4 2 4 4. Yes or no? Are present in R. So we will write down this solution over here. Since all the ordered pairs of C by C are present in R, okay, it implies all the elements of set C are related to each other. Clear? So this is the solution for the third question. First one was proving equivalence, that we have proved. Second question was this, and third question proving that in set C all the elements are related to each other. One more question is there, fourth question in the same question number 8. that no element of 1, 3, 5 is related to any element of 2 and 4. Yes or no? So that let us prove that. Okay, in order to prove this next question, I will remove these all the parts now. Yes or no? Okay, we have to show that now. The next question is show that no element of set B, that is 1, 3, 5 is related to any element of set C is equals to 2 and 4. Clear? So obviously which ordered pairs we have to check? If we have to show that the relation between B and C, any ordered pair exists from B by C, obviously we will find out B by C. Yes or no? That is B cross C, cross product of B with set B with set C. So you will find all the elements of the form odd even. Yes or no? For example, 1 2 1 4 and 3 2 3 4 5 2 5 4. So let us find out B cross C. You will get 1 2 1 4 3 2 3 4 and 5 2 5 4. Okay, now you can check each and every order pair. 1 minus 2 or 2 minus 1 is not even. 1 minus 4, 4 minus 1 is not even. Similarly, you can check that the difference of each or every ordered pair is not even. Yes or no? And therefore, we will say that none of the ordered pairs is present in R. Clear? Okay, so we will write down since none of the ordered pairs of B by C is present in R, and therefore no elements of set B is related with any element of set C. That's one. Therefore, no element of set B, that is 1 3 5, is related to any element of 2 4. So here question number 8 solution is 4. Clear? So there were total 4 questions in only one question, question number 8. Number 1, we had to prove that the given relation on set A is equivalent. So we have proved reflexivity, symmetricity, transitivity. Number 2, we have to prove that set B, okay, all the elements are related to each other, that is B by B. So we calculated B by B and showed that all the elements of B by B are present in R, and therefore the statement that all the elements of B are related to each other. Similarly, set C, all the elements of C are related to each other, so we calculated C by C and showed that all the elements of C by C are present in R, and therefore the statement that is all the elements of C are related to each other. The last question was this, okay, so that no element of set B is related to any element of set C. So we calculated B by C and showed that none of the ordered pairs of B cross C is present in R. Clear? And therefore no element of set B is related with any element of set C. Clear? So now let us solve the next question. We have completed question number 8. Now we will solve question number 9. A set A is given x belongs to z means set of integers, but not all the integers starting from 0 till 12. Okay, a relation, so that each of the relation given is equivalence relation. Two relations are given. Number one is R, is defined as A comma B such that A minus B is a multiple of 4. Okay. So, and the second question is also that we will write down afterwards. Let us solve this one first. Equivalence we have to show. It means reflexivity, symmetricity, and transitivity. So let us begin with reflexivity. Okay, here for all A belongs to given set A, yes or no? Modulus of A minus A is equal to 0 is equal to multiple of 4, because we know that 0 is a multiple of every number, and therefore we will say it implies A comma A belongs to R. Okay, yes or no? And therefore which order term you will check starting from 0, 0, 1, 1, 2, 2, 3, 3, 4, 4, 5, 5 till the last order pair will be 12, 12. So the difference of a number with itself is always 0, and 0 is a multiple of every number, and therefore A comma A belongs to R. Clear? And therefore we will write down that R is reflex. Clear? Now let us prove symmetricity. Okay. Now for symmetricity, we will take any two elements. A comma B belongs to set A comma B belongs to R. It implies modulus of A minus B is a multiple of 4. Let us take one example. For example, 0 comma 4, yes or no, implies 0 minus 4 is equals to 4 is a multiple of 4, which will imply 4 minus 0 is equal to 4 is a multiple of 4, yes or no? It will imply what? 4 comma 0 belongs to R, yes or no? So 4 comma 0 belongs to R we have taken. Then if 0 comma 4 belongs to R, it implies 4 comma 0, so its reverse pair. If this pair is present in R, then its reverse pair is also present in R, and therefore we will write down if A comma B belongs to R, then B comma A also belongs to R, and therefore R is transitive. Clear? Okay, now let us prove the symmetricity, transitivity. Number 3, transitivity. Okay, so here we will take 3 elements from set A. For A, B and C belongs to set A comma B belongs to R. It implies A minus B is a multiple of 4. Okay, this is number 1. Okay, and then another order pair B comma C belongs to R. It implies B minus C is a multiple of 4. This is result 2. So if the difference A comma B, the difference of two numbers A and B is a multiple multiple of 4, yes or no? Again 4 comma 8 belongs to R implies 4 minus 8 is equal to 4 is a multiple of 4. Yes or no? And therefore 0 modulus of 0 minus 8 is equals to 8 is a multiple of 4 only. It implies 0 comma 8 belongs to R, and therefore R is transitive, and hence R is an equivalence relation. Clear? So we have explained reflexivity, symmetricity and transitivity. All the three properties hold, and therefore R is an equivalence relation. Another relation is given: R is equals to A comma B such that A is equals to B. So let us solve the second part. Okay, so here we will write down the relation is given in this way: R is equals to A comma B such that A is equal to B. This is number 2. Okay, let us begin with reflexivity. Yes or no? So reflexivity can be explained in this way: for all A belongs to set A is equal to A implies A comma A belongs to R, and therefore R is reflexive. Yes or no? Since 0 is equal to 0, number is always, any real number is equal to itself. Yes or no? Here x is an integer from 0 to 12. So every integer starting from 0 to 12 is equal to itself. 0 is equal to 0, 1 is equal to 1. So we will have all the order pairs starting from 0 comma 0, and the last order pair 12 comma 12 are present in relation R, and therefore R is reflexive. So you can even explain like this. For example, 0 comma 0, 1 comma 1, 12 comma 12 belongs to R, and therefore R is reflexive. You can even add this one statement here to the solution. Now symmetricity. Okay, symmetricity. Obviously, in symmetricity, the same ordered pairs will come: 1 1 0 0 1 1 2 2 3 3. Yes or no? For all A B belongs to set A comma B belongs to R, it implies A is equals to B, which will imply B is equal to A, which will imply B comma A belongs to R. For example, 1 comma 1 belongs to R, it implies 1 is equals to 1, implies 1 is equals to 1, implies 1 comma 1 belongs to R. Yes or no? Hence the ordered pairs 0 comma 0, 1 comma 1, 12 comma 12 belongs to R, and therefore R is okay. These ordered pairs are only there, and the reverse pair reverse pair of 0 comma 0 will be 0 comma 0 itself. Similarly, for each and every ordered pair, the reverse pair of a given ordered pair is the ordered pair itself. Clear? So R is symmetric relation. Okay, now transitive relation. So obviously, since the relation relation, if you notice that all the identity pairs are included in R, because A is equal to B means only the ordered pairs starting from 0, 0, 1, 1, 2, 2, 3, 3, 4, 4, 5, 5 and the last order pair 12, 12. So these are called the identity pairs. So we know that identity relation is reflexive, symmetric and transitive. So in short you can explain by writing the relation R is equal to U, so that it is an identity relation. Why? Because all the order pairs starting from 0, 0, last order pair 12, 12 are present in R. Only identity order pairs are present in R. So every element of set A is related to itself only, and therefore R is identity, and therefore R is an equivalence relation. Clear? Okay. Let me explain the transitivity now. Okay, so transitivity will be explained in this way only. Okay, since order pairs 0, 0, 1, 1 and so on 12, 12 belongs to R, okay, and therefore you will notice that there is no ordered pairs of the type A, comma B and B, comma C present in R, okay, and therefore if A, comma B and B, comma C are not there, therefore we are not going to search for A, comma C, and therefore it is reflexive only, okay. Or in simple way, I have already explained you, write down the ordered pairs, write down R in terms of ordered pairs, yes or no, and so that it is an identity relation, and identity relation is reflexive, symmetric and transitive, therefore it is an equivalence. So in a short and sweet manner you can explain this question. Clear? Okay, so we will write down since A, comma B and B, comma C does not belong to R, or we will write down ordered pairs in ordered pairs like A, comma B and B, comma C does not belong to R, and therefore we do not find A, comma C in R, yes or no, and therefore R is transitive, or you can write down that R is an identity relation, and therefore R is transitive. Because while explaining the theoretical part, I have already explained that every identity relation is transitive. So since R is an identity relation, it is transitive, or this way also you can explain the transitivity. Clear? So the short way is to write down the ordered pairs of R starting from 0, 0, 1, 1, 2, 2, 3, 3. Clear? Let me explain you. Or you can explain this question in this way, or another method you can write down R, you can write down in terms of order pair 0, 0, 1, 1, 2, 2 and 12, 12. So it is clear from R that each element of set A is related to itself only, and therefore R is an identity relation. So by looking at the ordered pairs, we can say that each element is related to itself only. Okay, each element of set A is related to itself only, and therefore R is an identity relation. An identity relation is always reflexive, symmetric and transitive, and therefore, okay, an identity relation is always reflexive, symmetric, and transitive, and therefore R is equivalence. Clear? So this is the short method, and the previous one which we explained was a long method of explaining the same, second part of question number 9. Okay, I hope you have understood all the questions explained today in this video. Further questions we will solve in the next video. Thank you very much.